for those who are not able to attend, and I'm going to share my screen, and let me get back to your class. We're about to begin Module 4. We're kind of in the home stretch. So we are beginning Module 4, and the first lesson in Module 4 deals with correlation and linear regression, which is the parametric test. And then we will also talk about the non-parametric test, which is Spearman rank. We are scheduled to talk about this particular topic for the next 2 class meetings. I have posted an updated PowerPoint for correlation and regression. I have provided the Spearman rank PowerPoint and the examples in Word format. I do have, similar to the fill-in-the-blank notes that I had for hypothesis testing, I also have that same format for correlation and regression that I created initially during spring of 2020 when we were forced to go to online learning but due to COVID. And so I'm going to really kind of toggle between the PowerPoint and the fill-in-the-blank notes. So I hope you maybe have printed them off or have access where you can fill in the blanks as we go. But I'm also going to move between those notes and the PowerPoint related to correlation and regression. So if we're going to spend some time talking about correlation and regression, we kind of need to have an idea what we're talking about. So our focus in this particular lesson, it was a chapter is actually a chapter within the textbook, involves determining whether a relationship exists between 2 or more numerical or quantitative variables. Oftentimes, researchers are interested in whether there is a relationship, a connection, a correlation. If you think about that word, correlation, and I don't have a strong English background, but the prefix co means with, and then you have the word relation. So correlation gives us that connotation of with relation. So we're looking to see, is there a relationship between the 2 variables? Now, for our purposes, we are only going to look at 2. Most times researchers will look at maybe 4, 5, 10, 15 different variables at the same time and collect the data. And then in their analysis can look at the different relationships. And you can look at, 3 or 4 or 5 relationships at a time or between the variables. Again, for our purposes, we're going to keep it relatively straightforward, very simple, and we're only going to consider 2. We are considering 2 quantitative, which means there'll be numbers, variables at the same time. So some examples of where you might see correlation and regression used. A business person may want to know if the volume of sales for a given month is related to the amount of money spent on advertising. Is there a relationship, again, between sales and advertising? Educators may be interested in determining whether the number of hours that a student studies is related to their score on a particular exam. How much they studied for the midterm exam. Did that affect their score in any way, whether it might be a positive effect or a negative effect? A zoologist may want to know if the birth weight of a certain animal is related to its lifespan. Is the birth weight a good predictor of the animal's lifespan? Is there a relationship between the grade on the second math exam and the grade on the final exam? Is your income determined by your education? Is your income determined by your profession? Is your income determined by your years of experience? So there's lots of different variables there that we could consider. Think about medical research. Is caffeine related to heart damage? Is there a relationship between a person's age and his or her blood pressure? So again, the idea of correlation, and I'm going to go over to the fill in the blank notes. The idea here is used to determine if a relationship exists between two quantitative variables. The idea of considering two variables at the same time, that is sometimes referred to as bivariate data. And really, this is the first time in the course that we've looked at or considered more than one variable at the same time. Even with ANOVA, we were only looking at a single variable that was divided into categories by some characteristic. So this is really the first time we're considering two variables at the same time. And again, I hope that phrase bivariate makes sense. The prefix bi means two. Variate is the adjective of the word variable. So again, bivariate implies we have two variables. So notice it's correlation and linear regression. So we actually have two different procedures or two different processes that we're going to go through. The correlation procedure determines if a relationship exists between the two variables. So with correlation, we're asking the question, does a relationship exist? If a relationship exists, then we move on to the regression process. And again, for us, we're focusing specifically on linear regression. The regression process creates a model or an equation of that relationship. And then we can hopefully use that model to make predictions about what could happen in the future. Our focus again is going to be simply on linear regression, which is the simplest form of regression. I will tell you that you can take an entire course on regression. And within that course, you would talk about all of the different types, because you can have linear regression. You can have quadratic or quadrantial regression. You can have exponential or logistic regression. So there's lots of different forms. Again, we are only going to kind of touch on the initial one, which is linear. So that same information that I just walked you through is on the PowerPoint, and we'll get to this a little bit later, but I mentioned that correlation determines if the relationship exists. we're going to create or calculate what is called a correlation coefficient, which is a measurement of the strength and the direction of the relationship. And again, then the regression lets us create a model of the relationship. So again, that we just kind of walked through that, but it's on the PowerPoint. Again, our focus is on bivariate data where you have just two variables. We'll have what we usually call an X, which is a little bit of a carryover from algebra. It is considered to be the independent variable, or sometimes it's called the manipulative variable, because it's the variable that you as the researcher can manipulate or choose. In Minitab refers to the X, which is kind of, again, is like your input as the continuous predictor, because typically, again, it's going to be a number. So think quantitative continuous. Okay, so you're going to have a number and it's going to be continuous, most likely. The other variable is usually referred to as a Y and is the dependent variable. That is basically the result, okay, your output from the relationship. Minitab refers to the Y variable as the response. Your data is usually presented either as an ordered pair using the traditional format X, Y, but it can also be presented in a table form. And again, we're going to focus our attention simply on linear regression. And I've already pointed out that in real statistical research, they focus on more than one variable at a time. They do what's called multivariate or many variables at the same time, because that can also help to increase the time needed to do the research and the expense of the research by collecting a lot of data at one time. So as a reminder, and again, we'll talk more about this in a minute, from algebra, this is kind of one area of statistics where algebra and statistics kind of merge or come together. From algebra, we learn about the equation of a line, which is typically presented in what's called a slope-intercept form. Most students would say, oh, that's y equals mx plus b, where m is the slope or the tilt of the line and b is the y-intercept. Within statistics and within Minitab, they changed the notation just a little bit, and it's usually written y equals b plus ax. B is still your y-intercept. They use A to represent the average rate of change, which is similar to the slope. But with statistics, usually in algebra, we only have 2 points, 2 ordered pairs, when we create the equation of a line. In statistics, we may have 20 points. And so we're looking at all, it takes into consideration all of those points, not just 2 of them. And of course, the graph of a linear equation is going to be a non-vertical straight line. Okay, so that's just a little quick review, and we'll talk about it more in a few minutes. And we'll come back to that in just a minute too. So let's go over here and see what we can do as far as filling in some of our notes, because these notes are going to walk you through the procedure, much like the fill in the blank notes did for hypothesis testing. So we focus first on the correlation procedure, because the first question we're going to ask ourselves is there a relationship between variable 1 and variable 2? In fact, let me just write that question here. So you're going to be asking the question, is there a relationship between variable 1 and variable 2. Now, in terms of the word relationship there in that question, okay, we could see other words, okay? There are some synonyms you might see. You might see the word connection. You could also see the word correlation, the actual correlation word. Okay, so those are some other synonyms you might see in that particular question. So that's where we begin. We begin by asking that question, is there a relationship? So the first step is we have to identify our independent variable, which is typically represented by the X. And if you're looking at it in table form, it is usually the left column or the top row. If you think about it from algebra, usually when we draw a table, you would have X in the left column and Y in the right hand column. And again, so that's a carryover from that particular course. After we identify the independent, our second step is to identify the dependent. And that becomes easy because there's only 2 of them. So by default, the other one has to be the dependent, which is the Y. And guys, in terms of correlation, it really doesn't matter which one is X and which one is Y, because we're simply looking for a relationship. But it does matter when we begin to create the model, because we have to think about which one of the variables can we manipulate or choose, and that becomes our independent. So it's better to go ahead and identify which one is independent and which one is dependent from the beginning. Typically, the dependent is going to be in the right hand column or the bottom row. And again, that's kind of a standard across the board in statistics or even in algebra, is just that consistency that typically your X is on the left, your Y is on the right, or X is on the top, Y is on the bottom. Occasionally you'll find some folks that'll try to trip you up and switch them up. Again, I try to be consistent because that's the way you're going to see it. If you are struggling to identify the independent and dependent, I have a little saying that you can say, like, if we want to think about, do sales depend on the advertising, or does the grade on the test depend on the amount of time that a student studies? You can kind of use this little saying. Whatever you put in this first blank becomes your Y, or the dependent variable, and whatever you put in the last blank is your X, or your independent variable. So that little saying can kind of help you make sense of it. And again, if you think about it, I mean, if you try to reverse it, if we try to say advertising depends on sales, well, I can't really, I mean, advertising may affect sales, maybe not, we don't know. So again, think about it. Does the amount you study depend on the grade on the test? So sometimes you got to think about, does the animal's lifespan, or does its birth weight depend on its lifespan? Well, you don't even know what its lifespan is to start with. So just, again, that little saying there can help you, but you want to make sure that the saying makes logical, reasonable sense. Okay, so then step 3, and I'm going to go back over to the PowerPoint in just a minute to offer some additional explanation, is we're going to review the given scatter plot. Likely you will have to create one in Minitab to look at. Okay, we're basically going to start looking at it. There are really, once we've decided which variable is X, which variable is Y, then we want to try to answer the question, is there a relationship? And we start out in step 3 looking at it from a visual perspective. We are basically going to use our eyeballs to make a decision. So I want to go over to the PowerPoint for a minute and talk about what is a scatter plot and talk about how we create one. So a scatter plot is a graph that we're going to create. So it's a visual, and it's a visual interpretation of, do we think, what do our eyeballs tell us? Do we see some sort of pattern within the data? So a scatter plot is a visual method used to determine if a relationship exists. We graph each individual pair of numbers. So basically we're going to create a graph where you have your x-axis, which is the horizontal, and the y-axis, which is the vertical, and we would graph each of the ordered pairs, and then we begin to think about, does there appear to be a pattern within those dots? Okay, so it's a picture of the ordered pairs, and I have on a couple of slides over how to do it in Minitab, and we'll talk about that in a minute. But once we have that graph created, we want to ask ourselves 3 questions. Does there appear to be an overall pattern within the data points? And you're either going to say, yes, there appears to be a pattern, or no, there does not appear to be a pattern. Our next question is, does the overall pattern appear to be linear? Now we're asking this question because, again, we're only focused on linear. If we were considering any kind, we would say, you know, what kind of pattern do we see? But we're looking for a linear pattern. And again, this is going to be, yes, the pattern appears to be linear, or no, it does not appear to be linear. And then we ask one last question. Does the linear, or you could even say overall, pattern appear to be positive, negative, or 0? And in this case, what we're looking at is the slope or the tilt of the line. And there, from algebra, if you'll remember, there are 3 options. And I had those on the PowerPoint, so I'm going to toggle back over. Let me give you a minute to write that down if you're writing. Okay, so when you look at the scatter plot and you're thinking about, is the overall pattern positive, negative, or 0? Again, you're thinking about, does the graph move as you move left to right, does the graph appear to go up? Okay, so this is positive. They say it as the M, or the slope, is greater than 0. Does it appear to go down as you move left or right? When it appears to go down, that's negative. So M is less than 0. Or does it kind of appear to be a flat line again as you move left to right? A flat line has a slope of 0. Again, you probably won't see that one in the middle very much. Most likely you're going to see either a positive or a negative. Now, guys, they're not, when you're looking at these scatter plots, it's not necessarily going to be dead on perfect straight line. Okay, let me show you some examples. So, for example, these are some different patterns you might see within scatter plots. This first one says you have a positive linear pattern, so that you would have what they call a strong correlation. Again, look at the dots, and as you move left to right, it does appear to go up. Okay, so that's why it's positive. And it appears almost like the dots are in a perfect straight line. So that would be a positive linear pattern, and it would have a strong correlation, again, because it's almost a perfect straight line. You could have something like the one on the right, where you have a linear pattern, except for this one little kid or one little dot that's way off over here by itself. You've got that one deviation. Okay. You could have a negative pattern. Again, negative because it goes down as you move left to right. Again, this one would be somewhat of a strong pattern because the dots appear almost to be in a perfect straight line. The one on the right, you have just random dots. It does appear to go down as you move left to right. We could probably imagine a line going through some of those points, but because they're so scattered, we would consider the relationship weak. Finally, you could have a pattern within the dots, but that pattern may not be linear. This one is actually what they call exponential. You could also have something that perhaps looks more like a parabola. So that would be more of a quadrantial growth pattern, okay, or a quadrantial pattern. It's still a pattern, but it's not linear. Or lastly, another option would be that there's no pattern at all. There's no rhyme or reason. It just looks like a bunch of dots on the page. Okay, so again, that gives you an idea. And the thing is, guys, with a researcher, there are 4 of us in the Zoom room, and all 4 of us could interpret or look at that scatter plot and have different opinions. Okay, because we could see it differently. I might think it's a strong relationship, and Ainsley might think it's just an average relationship, and Naomi may think it's a weak relationship. Okay, so we can have disagreement because we each have different eyeballs and we're seeing it differently. So we don't typically rely on just the scatter plot. Okay, so visually we're going to make a determination using our eyeballs. We're going to kind of answer questions. Is there a pattern? We're going to say yes or no. Does that pattern appear to be linear? Again, we're going to say yes or no. And then, is that overall linear pattern positive, negative, or zero? But we don't stop there, again, because we could have disagreement because we're using our eyeballs. So the next step in the process is we're going to look at it more so from an algebraic perspective. And the algebraic perspective will leave no doubt. Once we calculate that value, we all four of us would have the same value, and we would have to interpret it similarly. So that if there is discrepancy, the algebraic perspective is going to remove that doubt or that discrepancy. So we will use Minitab to calculate what's called the sample linear correlation coefficient. Now, again, we're dealing with a sample, but there does exist the population linear correlation coefficient as well. And we use the same pattern for the sample. The symbol is the English letter R. For the population, we use the Greek letter, and it's the Greek letter rho. Okay. Now, let me give you some background on this particular thing. The correlation coefficient actually has a fancy dancy name. It's the Pearson product moment linear correlation coefficient. It's actually named after Carl Pearson, and it is a numerical measurement of the strength and direction of the linear relationship. And I'm sorry, I do have relationship misspelled there. Let me stress to you that this measurement, the sample linear correlation coefficient, or the Pearson product moment linear correlation coefficient, whatever you want to call it, is only used for linear relationships. It's only used to determine if there is a linear relationship, the strength and the direction of a linear relationship. So what that means is if you have one of these things that doesn't appear to have a linear pattern, I'm probably not going to use the linear correlation coefficient. There would be other options, because the linear correlation coefficient only considers or only calculates the strength and direction of a linear relationship. Okay. I've put the formula here on the PowerPoint, but again, that numerical measurement is going to quantify it for us so that we're no longer relying on our eyeballs. We get a number. And guys, the calculation is just woo, because you would have 1, 2, 3, 4, 5, 6, 7 preliminary calculations before you ever plug it into this formula. And the formula is a fraction, which everybody loves, of course, and involves the square root. I mean, it is messy. And when I learned it, I would have to sit and create a table, and I didn't have Microsoft Excel to do it, or I had a handheld calculator basically. And so you would have to calculate all of those values and create tables to do it. So you guys have a much better chance of getting it correct and doing the problem because we're going to use Minitab. No researcher in their right mind is going to do those calculations by hand anymore. Okay, but I'm going to tell you a couple other things, and I couldn't remember what was next. Okay, but going back over here into the fill in the blank notes, the other thing about R that is going to be important to us is that the R value is between -1 and +1. And that's also true if you're talking about it in terms of the population correlation coefficient as well. Okay, now let's talk for a minute about what that means. Okay, what would that look like if I were looking at a scatter plot? Okay, so if you think about this like a graduated scale, okay, you have -1 on the left, +1 on the right, and then in the middle you have 0. If my R value is -1, okay, visually, if my R value is -1 and I'm looking at the scatter plot, it would be one of those scatter plots where it appears that my dots or my data have lined up in a perfect straight line. This would be a perfect negative linear correlation. Again, your dots or your data would appear to be in almost a perfect straight line and would be going down as you moved left to right. If you were at +1, again, you would have the dots in almost a perfect straight line, but they would appear to go up as you move left to right. So that would be a perfect positive linear correlation. If your R value is near 0, one of two things is happening. Either you don't have a linear pattern. You could have a pattern, but it's not linear, or you have no pattern at all. And the deal is, guys, I can be any value in between. It is going to be very rare that you're going to have a perfect negative linear correlation or a perfect positive. But as I move out from 0, as you move to the left towards -1, the closer you are, the stronger the relationship. As you move to the right towards +1, okay, you basically go from weak to strong, and then you have moderate. And different folks are going to interpret those differently, and I think I do have some information for you on that on the PowerPoint, so we'll get to that. But again, that the R value should always be between -1 and +1, and this gives you an idea of what that means. The direction is determined by whether it is positive or negative. The strength is determined by the numeric value, how close you are to 1. Okay, let me see what else that's the stuff on how to do it in Minitab. Okay, so that's what I've got left on the PowerPoint is how to do it Minitab. So after we've calculated our test statistic, or not our test statistic, but calculated our linear correlation coefficient, we can definitively say, yes, there is a relationship, or no, there's not a relationship, but we want to be able to say that without doubt. So we have to go one step further. Remember, we got to think about it. Is it statistically significant? Is it different enough from 0 or close enough to 1 to say, yeah, there is definitely a relationship? And the way we make that determination is we are actually going to do kind of a modified hypothesis test. We have to determine if R, which is the linear sample, I should say, sample linear correlation coefficient, R, is statistically significant using a modified hypothesis test. So we're not totally getting away from hypothesis testing. We use a hypothesis testing within the context of correlation to determine if our correlation coefficient is statistically significant. Again, is it different enough from 0 or close enough to 1 or -1 to say, yeah, there's definitely a relationship? So let's walk through the steps here. We begin, as we always do with any hypothesis test, by stating the hypotheses. You still have a null hypothesis. The null hypothesis for the sample linear correlation coefficient will always be rho, which is the population correlation coefficient, equals 0. Okay, remember the null hypothesis must always and forever contain equal. But to be equal to 0 in terms of our correlation coefficient, that means there is not a linear correlation and R is not statistically significant. Now, guys, notice that because that seems backwards. A lot of students get that confused. But if we're close to 0, 0 means we either have no pattern within the data values or we have a pattern that is not linear. Okay, so it seems a little weird to say that. The alternative hypothesis is that rho does not equal 0, which means there is a linear relationship or a linear correlation. Let's use correlation to be consistent. There is a linear correlation and R is statistically significant. Okay, then we're going to use Minitab, and Minitab is going to do the test for us. And I'm trying to remember which test it is. I'll have to look when we go into Minitab because I don't remember. Determine only the p-value. I don't really need the test statistic here. All I really need is the p-value for the test statistic. Now, if you record the test statistic, I'm not going to get upset, but you don't need it. All you need is the p-value. And then we're going to do our usual thing. We're going to make a decision to reject the null or fail to reject the null by comparing the p-value to the level of significance. That part is not going to change. We typically use alpha equals 0.05. And then based on our decision, we're going to make our conclusion. And our conclusion ultimately is going to be, is R statistically significant? Because that's what we need to know. Is R statistically significant? And ultimately, we're going to say, yes, it is, or no, it's not. Which then leads us to step 6 to conclude if there is a correlation or a relationship between the two variables. And again, this is going to be a yes or no answer. Okay, so at that point, once we have reached step 6 in the correlation process or procedure, we have determined without a doubt whether or not there is a relationship or a correlation between the two variables. Okay, so here's the deal. If you answer yes, there is a relationship, then you're going to continue to the linear regression procedure. If you answer no, then you stop, because there's no point in trying to create a model or an equation of a relationship that doesn't exist. So then the question becomes, well, how can I make predictions from that data? Okay, if you're not able to create the model because a relationship does not exist, we use the average or the mean of the Y values for prediction purposes. We just revert to saying it's going to be average. Okay, so let's assume that we have said, yes, there is a relationship. So then we're going to determine the linear equation or the linear model in the form Y, and usually we'll put a little tick mark next to it. It's read Y prime equals B plus AX. Okay, where B is your y-intercept. I mentioned this a minute ago. And A is your average rate of change, which is similar to the idea of slope. But the difference is, for average rate of change, I have considered more than 2 points. We use that little tick mark, this Y prime, okay, is a way to indicate that we statistically created the model, that we used, a data set with, 5, 10, 15 pairs of data. Okay, that's just the notation we use to indicate that we have the statistically developed model. Another symbol you might see, some texts use Y and they'll put like a little V or a hat on top of it, and it's read Y hat. it's the same thing, but again, it's just a matter of which textbook you pick up, what researcher you're working with, perhaps how they learned it. But again, Minitab is going to do all of this for us, okay? You're not going to do this by hand because the formula for figuring the y-intercept and the average rate of change when you have 5, 10, or 15 data values is messy. Be thankful you have the technology. Okay, then we're going to use the linear equation model to make a prediction for a given a value for the independent variable. And I don't know what the and is. Guys, basically this step 2, it is a kind of a hand calculation, but you're plugging and chugging. You're going to take the value that you're given and substitute it into the model. You're plugging and chugging. Now, we do need to talk about what values can you use. And let me see if I can scroll down, or I'm going to toggle over to another page. Okay, there are 2 types of predictions that we can do. Okay, there are 2 types of predictions that we can do. One of them is called interpolation. And the other is called extrapolation. Again, if you know a little bit of English and some of the prefix issues, intra means between. Okay, so interpolation means that we're going to use a value between the minimum and maximum given or known values. So we pick a value, and it can be one that you already know, but you're going to plug it into the model, but you're going to use a value between the minimum and the maximum given value. You stay between the fence post for your high and low. You choose a value between those. Extrapolation, extra in this case kind of means outside. So extrapolation, we use a value outside the known range of values. So we pick a value that's maybe a little bit more than our high value or a little bit less than our lowest value. But with extrapolation, you have to be very, very careful, because if you go too far beyond that known range of values, your model could break down, meaning the model ain't gonna work because you only know about it from point A to point B. If I go very far beyond point B, that model may not work anymore. Something may change. And so the model is called the model breaks down. So you have to be careful about extrapolation. Ideally, you want to do interpolation. Okay. One of the other things that we look at once we've created this model is we want to decide, and I suppose really we should decide this earlier on, is it even appropriate? Should we even use the X value to predict the Y? For example, there was a problem in a textbook years ago that looked at the relationship between ice cream sales and the murder rate. And quite honestly, there was a relationship between ice cream sales and the murder rate. But that's not necessarily a good predictor. Ice cream sales is not necessarily a good predictor of the murder rate. I mean, think about it. Typically, ice cream sales are going to go up when it's warm or hot. And when people get physically hot because of the temperature, they, tend to maybe get angrier or fly off the handle more. And so the murder rate tends to go up. So the fact that ice cream sales go up doesn't necessarily mean that murder rates are going to go up. So we have to stop and think, well, yeah, we've developed this relationship, but is this relationship a good one? Is using ice cream sales a good predictor for murder rates? Is using the amount of advertising good for predicting the amount of sales? And so we look at what is called the coefficient of determination. And it is represented by R squared. Okay, it is R squared. So it's the square of our linear correlation coefficient. And again, we're going to basically answer yes or no. And this is one area where we're going to kind of wave our hand a little bit. There are other more in-depth statistical analyses for making this determination, but we're going to stick with the rule of thumb that if R squared is greater than 50%, we're going to say, yes, it's a good predictor. Now, again, that's a little bit of waving our hand. We're not going to go through another statistical process. I'm not going to add another process to it. Okay, so if the R squared value is greater than 50%, we're going to say yes, that the X value is a good predictor of the Y value. And then the last step is to interpret that coefficient. Oops, spelled that wrong. Sorry. Coefficient of determination. And guys, the sentence is the same every time. The piece that changes is the variable. So approximately R squared percent of the variation. And guys, you have to put in the word variation. Variation in the Y or the dependent variable is determined by the variation in the X or the independent variable. Okay, I've got about 14 minutes. I would like to try to start example 1. I don't know if we can get all the way through it with all of the explanation, but let's see if we can start. And the examples are at the end of those fill in the blank notes. So it says the following are advertised sale prices of color televisions at an electronics store. So in the table, you're given the size of the television in inches and then the sale price. So the question is there a connection between the size in inches of color televisions and the advertised sale price? Now, again, because Miss Ralston has told you that she's reasonably consistent, it is likely that the top row, which is the size, is our X, and the bottom row is Y. Let's check that and see. Does it make sense if I say the sale price, which is Y, depends on the size? Or do I need to turn that around? Should I say size depends on the sale price? That doesn't really make sense to me. This statement, sale price depends on the size of the TV, that makes reasonable sense. Okay, so based on that, and not just relying on what I know about the table itself, the sale price is going to be the Y because the first one is your dependent and the second one is your independent. So my independent is going to be the size in inches of TV. The dependent is going to be the sale price, and it's in dollars. Then we need to create a scatter plot. Now, the instructions for creating a scatter plot are on slide 13 of the PowerPoint. Okay, slide 13 of the PowerPoint. But the first thing I'm going to have to do, as we do with anything, is we're going to have to enter the data. And we do have two distinct data, or two distinct variables. So I'm going to put the X in column 1. And notice I went ahead and labeled it as X, okay, because that's going to help me later. And then next to it, I'm going to put the sale price, and I'm going to label it Y. And again, that'll help me later on. So I go ahead, once I've decided which one is X and which one is Y, notice that I did label it on my table, and I've labeled it in Minitab. Again, that just helps me to keep it straight. You have to keep the data paired as it's given to you. So I'm typing the data in. Again, you will, when you're done, you will have two columns of data. Two columns. You'll have one column for the X, one column for the Y. Now I'm going to create my graphs. My graph. So it's a graph. So we go graph, scatter plot. We only have one Y variable, and we're going to keep it simple. My Y variable, see, Minitab asked me to identify the Y. Well, because I labeled it, I know that sale price is my Y, and the size of the TV is X. So I choose my Y, I choose my X, and I tell it OK. And we get this scatter plot. So let me bring it over here to the paper. Okay, so here's our scatter plot of the size of the TV to the sale price. And we're going to ask ourselves 3 questions. First question, does there appear to be a pattern in the dots? What do you guys think? I would tend to say, yes, there is a pattern.
Yes, like a slightly, maybe a weakish one.
Probably
but
a weakish one.
Yeah.
It almost, to me, then the second question says, does it appear to be linear?
It almost
And
seems exponential, doesn't it?
yeah, it almost looks exponential, but we could maybe see one going up through there like that. Maybe. You know, so you could debate, we could debate it. And again, because, you know, I'm saying yes, Jeannie's saying, I don't think so. Remember, there's going to be that disagreement, and it's okay. Okay, because that's your interpretation. Okay, so this is almost kind of like a maybe. And then, but I definitely can see that regardless of the pattern, it does appear to go up as we move left to right. So the overall pattern would be positive. Okay. That's our eyeballs. And again, even though Jeannie and I disagreed maybe over the overall pattern, whether it was linear or not, it's okay. Again, because we're relying on our eyes and people see things differently. But then we go to the next question and to the next step, and we're going to actually calculate the correlation coefficient. And hopefully at that point we'll have no doubt. Okay, so here's how you get your correlation coefficient. The instructions are on the mini tab on slide 14. So we're going to go stat, basic statistics, and we're going to scroll towards the bottom for correlation. Stat, basic statistics, you have to scroll down to correlation. I just need to tell Minitab the 2 variables I want it to correlate. So we've got size of the TV and the sale price. It does not matter the order that you select them in. I do need to choose options. We want it to do Pearson correlation. We'll come back on Thursday and talk about Spearman. Okay, so you want to make sure you have Pearson and that it's at the 95% confidence level. We just default to 95%. I click OK. I click OK. It gives me the same plot, okay? And in 2 different places, it gives me the correlation coefficient. It does provide the R value at the bottom of the graph. See, it says R equals 0.894. Or if I scroll down to correlations, okay, it gives me the correlation between the sale price and the TV. And we get the R value is R equals 0.894. Now we're going to run the hypothesis test in a minute. But remember that that R value should be between -1 and 1. And honestly, 0.894, if you think about it, that's going to be over here reasonably close to 1. You know, so originally, Jeannie was thinking it was a weak linear relationship, but this value seems to indicate that it's more moderate to strong. But there again, is it different enough from 0 or close enough to 1 to be statistically significant? So then we're going to conduct our hypothesis test. And let me see if we can get through this piece here, and then we'll stop. Okay, so our null hypothesis is always that rho equals 0, which means there's no correlation, and R is not statistically significant. The alternative is that rho does not equal 0, which means there is a correlation and R is statistically significant. The directions for doing this are on slide 15. And guys, this process for finding the p-value for your modified hypothesis test is also going to give you the model and everything else you need. Okay, Minitab has it all kind of grouped together under one thing. So here's how we do it. Stat, regression, regression, fit regression model. My response is Y. My continuous predictor is X. We tell it OK. Now, guys, we get lots of information. The piece I need, let me make sure I get to the right one, is under the header analysis of variance. So we're actually looking at analysis of variance. Okay, so I'm going to copy this. And what we're looking for is this p-value right here. Notice it's the same for both of them. So my p-value for my hypothesis test where we ran an ANOVA is 0.007. If I compare the p-value to the level, and I know it's 1215, significance, okay, so we have 0.007 to 0.05. When you make that comparison, the p-value is less than the level of significance, which means we're going to reject the null. Remember, if you reject the null, that means the null is false. And by default, that means the alternative is true. If the alternative is true, then the R is statistically significant. So because we rejected the null and the alternative is true, R is statistically significant, which means there is a linear correlation between the size and the price of the TVs. Now I'm going to stop there because it's 12:16. I do apologize for running over. Okay, but we'll stop there and we'll pick back up and go to the next step on Thursday where we create the model. Again, I apologize for running a minute over, but if you do have questions, I'll try to answer those before we go. All right, guys, I will see you Thursday morning then.
Thanks. Y'all have a good week.
You too.